Oh, and Emina, after the seminar, the recorded talk will be posted on YouTube. That's okay with you, right?
Yes.
So more people will watch it later. Okay, I think we can get started. Good morning, everyone. Welcome back to the SNAPP seminar series. This is the second seminar of the semester, and we will have more seminars coming up every 2 weeks. Today, we are delighted to host Professor Emina Soljanin. She's a distinguished professor of ECE at Rutgers. Before moving to Rutgers, she was a distinguished member of technical staff at Bell Labs for more than 20 years. And her interests are pretty broad. They range from distributed computing to quantum information science. And she has received many awards and honors, including IEEE Fellow, Outstanding Alumnus of Texas A&M, Padovani Lecturer, Distinguished Lecturer, and she was also IEEE Information Theory Society's President in 2019. And most recently, Emina received the Aaron Weiner Distinguished Service Award from the Information Theory Society. So it's a pleasure to host her. Today, she's going to talk about diversity and parallelism in distributed computing with redundancy.
Thank you, Gauri, for this nice introduction. And I'd like to thank all organizers for inviting me and all of you who are here. So I'm going to talk about one aspect of introducing redundancy in distributed computing. And when we hear the word redundancy, to some people, it means something, there is some negative connotation, right? But it should not be like that. And this work is a joint work with my former student, Pei Peng. He's now a professor at Nanjing University. We are very proud of him. He got that without even doing a postdoc. And my former colleague from Bell Labs, Phil Whiting, who is now a professor in Australia, but he was visiting us in 2019 when we started talking about this. And here is a cartoon which I will continue at the very end of the talk. And here is the boss of Dilbert who is asking, how long will this project take if I add 2 people? So this is a boss who actually would like to add some redundancy among the workers, but usually bosses don't like that. So my job at Bell Labs has been to push codes into products, those that I designed and some other people designed. And of course, all the Information Theory Society and friends from there were cheering because we really did, during my tenure at Bell Labs, put lots of codes into products. But then again, there are these deciders who are skeptical about the value of redundancy. And I'm not going to advocate for either. I'm just going to say that we really need to examine this value. So there are some questions maybe in the chat or something popped on my screen. I don't.
No, that was just the link to your slides, Emina.
Oh,
no questions in the chat. Yeah,
thank you. So what is a coding game in coded computing? So coding is a specific form of redundancy that we use in physical layer. On the physical layer, all you need to do is plot some pictures like this, which tell you how adding redundancy in some controlled way can help you use less power and achieve better error rate. And even in these in the physical layer, there is a range here where actually adding redundancy is worse than not adding it. With this particular form. There are fundamental theorems in information theory which will tell you for any signal-to-noise ratio, there is some optimal code, and obviously this one is not here. Things become much more complicated in computing because although we know that codes provide fault tolerance and may be helpful in struggler mitigation, they also slow down storage and repair. and may change traffic patterns, they invalidate various independence assumptions, and they obviously require additional resources. So coding gain is not clear. And in the physical layer, you will get a simple question asking you which in this class of codes, some of you will know what this is, there is some class of codes, will guarantee certain bit error rate. And all you need to do is plot those figures that I show in a little bit different form and give them an answer. And even then, it wasn't easy to argue for use of codes, although they're of course now everywhere. In a computing system, the question is a little bit different. It asks which code will guarantee that the probability of a computing job taking longer than t does not exceed some value. I have just put here 10 to the minus 12 because that's what I had in this question before, which really came from a business unit at Bell Labs. And all that has to be at some lowest computing cost. So you don't want to run your tasks long, right? And that's why we, in distributed computing, we split them into, we split jobs, so that's a terminology, we split jobs into tasks. So tasks, these are sub-jobs that I'm going to be calling here, to allow parallel execution. So one example is MapReduce. I will be using a little bit different architecture later. And then task completion, or service time, computing time, is random. And therefore, job completion tasks, so therefore, all these tasks will be completed at different times, these tasks that your job is split into. And job completion time is determined by the slowest task completion. And some of these tasks can be very slow, or they can exceed some time tau. And such tasks we call stragglers. I don't think I will use that term a lot, but let's say that some tasks, that's tasks that exceed some time tau. And if you put in diversity, then if you put in redundancy, then you will get diversity. So task redundancy will provide tolerance to stragglers. And so both parallelism and diversity shorten, or can shorten, or have potential to shorten job completion time, but they compete for resources. So what would you go with? If you have 5 servers, would you split your job in 5 and have each server do 1/5? Or would you split your job in 4 and have each server do 1/4 of a job, but the last one can be used for the diversity? So that's the type of a question. I, of course, will define it more formally. But before that, here is another prologue to diversity versus parallelism. So here I have clouds, and I have a person I want to fetch some water. And it starts raining, the water comes out, but from 2 clouds where I am not at. So I figure out I should diversify. So I should go under all clouds, and it starts raining, and at some point, both of them are full, but I only need one, and maybe the other one is not even completely full, so I'm throwing that away. And so I can say, well, maybe it's better than to go to some smaller cup, then I'll be done sooner. I will have to get back both cups, but this will be done in parallel. And that may be good. Or even better, maybe I can increase this parallelism and go with the 4 small cups, and that will be even faster to fill. But that, of course, depends on how these clouds behave. So this first picture here is replication. This is my maximum diversity. The second one is coding. That's where I have a trade-off. And then the last one is splitting, and that's the maximum parallelism. And so this is just to tell you what this question is about, but of course we'll define this formally. So in this particular system that we are going to consider, and these are common architectures, for example, Kubernetes and some other. You have a controller node and you have n workers. And here I have plotted 4. And then this controller splits jobs into n tasks. And here I put a number of tasks and workers identical to, because I don't have any more workers, right? And I can also possibly generate some redundant tasks. And then I will dispatch these redundant tasks to workers. So in this first example, in both of these examples, I have a job that has 4 tasks. And in maximum parallelism, I would give one of these 4 small tasks to each worker. So this is the strategy 1. In the replication or maximum diversity, I would give this entire 4 tasks or entire job to all of the 4 workers. And in coding, it would be something in between. So what is here? What is here the contention or between one strategy versus the other? So here I have smaller jobs, but I have to wait for 4. Here I have a little bit bigger jobs, but I have to wait only for 2 out of them. And of course, here I have to wait only for 1, but that one has to do all 4. So what is the best? And this is what I said. The first one is splitting, replication, or coding. And this coding is a trade-off. Like, what is the best level of redundancy? So what about codes in distributed computing? So very often people will tell me we have these codes. So there have been lots of work on designing codes, right? So essentially they now exist at all rates and any computing job, but what good they are if we don't know which one is good for our system. So this is like having a big choice in a grocery store that you want something, right? But you really don't know, like say a table, what is the best for your kitchen, right? And even when we have codes, there are various things. And I'm more a coding theorist than anything else, right? So, but we have to admit that even when codes are there, we have to answer questions like, should coding or replication be used? If I'm sending redundant tasks, when should I issue this redundancy? Should I cancel some of them, thinking they're stragglers? When that canceling and relaunching should happen? And such questions are there. I am only going to focus on how much redundancy essentially to use on this diversity parallelism trade-off, which is the title of my talk. But there are various these other questions, which I may touch upon at the very end if there is time. So let's now start a little bit defining things. So I'm going to have computing jobs that are split into tasks for parallel execution, but there is some notion of some minimum task, which I'm going to call computing unit, CU. So beyond that size, distributed computing is inefficient because of some systems overhead or some other things. So for example, here I'm multiplying a matrix, which I've split into 2 and 1 row, and I'm using it to multiply this vector V. And it would be natural to think about computing unit as just single row multiplying this column vector, because if I send half of a row to one worker and half of the row to another worker, there is still work that I have to do, right? Whereas if I'm just multiplying this one row with this one column, I already have one entry in my result vector. So I often say this is me in the United States here with a big cup of coffee, and this is me in Europe with numerous little espressos. And if you compute, it seems that you need 6 espressos for a small Starbucks coffee, right, in caffeine. But is this all that, you also, someone has to wash these little cups, etc. So what I'm trying to call your attention to is that collecting these computing units into one task, it doesn't mean that this pink task here is twice as fast as this green tasks. So this is 2 rows, this is 1 row, but it is in general not twice as fast. Maybe it's adding 2 random variables that are statistically identical, or maybe it's something else. So we are going to be measuring the number of jobs by this number of computing units. So here we have job size 3, and it's split in 1 task of 2, size 2, and 1 task of size 1. So this is just for this example. We were going to be splitting jobs in equal size tasks. Okay, so job of size n, so n computing units, are split into k tasks. I cannot go below n, but I cannot split them in more than n, but I can split them in fewer. So here I have split my job of size 4 into 4 tasks. Here I didn't split, or split into 1. Here I split in 2 tasks, and then I'm adding coded tasks. So the smaller the k, the larger the task, right? If k is 1, it's a complete job. If k is n, it's just the smallest, the computing unit. But then, so that's good, but then fewer workers have to complete their task for job completion. So the larger the task, the fewer the workers have to complete the job. And so this is this trade-off between diversity and parallelism. That is dictated by k. So the parallelism is increasing k, and the diversity decreases with k. So what is the optimal k for a given service time and task execution model is what we are going to talk about. So I don't know now if there are any questions.
If anybody has questions, feel free to either write them in the chat, or you can also unmute and speak out the question.
And if you don't, I will continue, and Gauri will interrupt me if she sees something in the chat. So service times that we are going to consider are what people considered in papers in connection with redundancy or computing in general. The canonical ones are shifted exponential, for which is going to be the focus of this talk. And the other two that we considered are Pareto, and this is something we called simple bimodal. I called it bimodal, but then my students started calling it simple bimodal. I don't know if there is a standard name. So the first one I'm going to talk about here, and the other two are in the paper. I'll tell you what the paper is. And this bimodal is because you must have seen some such pictures in literature that if there are, I don't know, here I think there are 50 workers, and most of them, at least 40, finished in some unit time, and the rest of them, 10 or so, took B times longer. So this fraction of 10 is one. I don't know if it's 10, but let's say 25% or 0.25 is this epsilon. So probability that you'll have a longer execution is epsilon. And if there is only one computing unit to be addressed, executed, and you have multiple workers working on it. I have here 6 servers working on one computing unit. Then in this example, each one has an exponential or coin tossing clock, if you prefer that. And the worker is done when the clock shows head, right? And it will show head through some coin tossing mechanism. Or for most of the people on this call, they'll probably know exponential, but can see it as exponential clock. So they start, the clocks start working, or coin tossing starts, and they all start working. And at some point, one of them says, "Oh, I'm done." And that will happen with some probability, right? And this is a geometric random variable, this waiting time. And its probability of success is not pH anymore, but 1 minus probability that no one succeeds. And I have 6 of them. And so I'll explain this notation later. So this is expected time is about 1/6 of, for small pH, of the original. And then what happens is everything starts from the beginning, because this is a memoryless system. And I have now 5 workers, and the first one finishes at time 1/5 and so on. So then all of them finish. And at the end, I have, after k of them finish, is the sum of these random variables. And these random variables are order statistics. So what I'm asking here is, how long does it take to execute k out of n of these computing units? And if I have a collection of random variable n, then the kth smallest among them is the kth order statistics, is also a random variable. It has this notation, and for some of them, like exponential, these expressions are known. Okay, so it's interesting that for the exponential, the first order statistic, the first time one of these 6 coin tossers get head is the expected time divided by n. By the time the last gets is the expected time times log n, approximately. So that's the range between the first and the last in expectation. But we are not executing only one computing unit. We are executing multiple of them. And that is when the things become a little bit more interesting and unknown. And that is what it really means. Is it drinking from 1 cup the same as drinking from 6 cups? Here there are 8 actually. Maybe for some people who don't put sugar, right? I don't, like you just drink 1 espresso after the other, and you know, it's at the same time. But still you have to put down this, right? Cup, right? Maybe some people who are putting sugar in each one, that time is random, etc. So we can also discuss that in terms of thinking about going to a grocery store. And sometimes you just approach a person, a server, a cashier there, and you talk a little bit with them, with some longer, with some shorter, depends on what kind of mood they're that day, or what, how much they know you, etc. And then they just go. One item after the other is the same. Then there might be another model in which each of these servers, one is saying, for each of this item is completely independent. It takes the item, reads a little bit, oh, this is nice. You know, sometimes, especially in Trader Joe's, people comment on what you buy, and oh, I like this, last time I had it. So every item is completely independent. Or it may be that servers, which I said they all have in the beginning, depending on how much you know them, they have some initial handshake, but once when they start, they're identical, but they may not be. Some of them are consistently slower, and some of them are consistently faster. And so we have 2 models, 3 models, which I'm going formally to define. But what I was saying is there is something that's server dependent, and for there will be some handshake which is constant, and then that in the computing job may depend on data, and then there will be this first one which is kind of medium. There is this second server which is really fast. There is the third which happened to be slow, and then the medium one, the first one. But between each of these, each computing unit is executed it takes the same time for the execution. It just depends on which server you are. And then for data, this picture is the best illustration I can master. There is some handshake which sometimes is short, sometimes is long. But then how close these ticks are, it depends really on how much you split your data. So if I had a fourth line here, these ticks will be shorter. And then there is an additive where each time is random, and they add up. So the first one for the first worker, for the first server took long, for the first short, but then, it changed, etc. And so formally, we are asking if it takes some exponential or Pareto or bimodal time to finish one unit, how much time does it take to do S? And there are some reasonable models which people throughout the literature have used. One is what we call the server-dependent model. There is some constant time plus something that's changing depending on how much you assign to each worker. And that may be most often used in the, at least coding literature, just to make some conclusions. Then there is a data dependent where actually there is some random time associated with server. This is this cashier that talks in the beginning with you, but then later everything is constant. But it depends how much time he has to do. It depends how many items you have, right? So that is this S here. And then finally, there is additive where for each task, for each cup here, let's say, it's an independent time and it adds up. And it's interesting that this is summary of the results, and then I'll tell you a few, maybe a few proofs for this, is the following, that if you look here at this three distributions, shifted, exponential, Pareto, and bimodal. And on this side, you have the scaling, whether multiple computing units are executed in a server-dependent time versus data-dependent versus additive, then there are different results. So in this talk, I'm going to talk about this column a little bit, and in the paper, there are these two. So what it says is, if it's server-dependent, then the replication is optimal. There is no reason to split. If it's data-dependent, then you start from splitting to coding to replication. And if it's additive, you should not do replication. So now you start. What this arrow means is that all those distributions have certain parameters, and going along the errors, meaning that parameter changes in a way that the tail becomes heavier. So there is more randomness. So of course, in the beginning here, you have splitting, because if you have not much randomness, there is no reason to introduce diversity. But if you have lots of randomness, then it's good to have replication, right? So some of these things are, there is some sanity check that you can do and say, do these results make sense? But there are also some surprises, especially when you move out of the exponential, for which we don't often have good intuition. All right, so this is the model and the summary of the results, and now I'm going to prove some things by animation more than, well, not exactly. So before I start that, if there are any questions. Okay. So server dependent is actually easy. So task execution time becomes random. If you split your job into k tasks, so you have n. Very often in the paper we have 12 because it has lots of ways to divide it. You can divide it in 6, in 2, in 3, and 4, right? And in 12. So if you split it in k, then the size of each task is n over k. So if I have this 12 and I split it in 3, size of each task is what do they say? Split it in 3, size of each task is 4. If I split it in 4, size of each task is 3. So S is the size of the task, and the model for this server dependent is that now each worker or server draws from this distribution. And that is just simple application of these order statistics formulas that I mentioned, and the equality is achieved for this expression when k is 1, and therefore replication is the best. And that is because you actually have, in this kind of models, lots of randomness. And things change. So this is for the exponential. And it's not true for Pareto and bimodal. Right? So depends on the distribution, and also depends on how these tasks scale with the size, how execution scales with the size of the task. In data dependent is something that I think is something Gauri and I used maybe 10 years ago, or something similar in some different context. You have a part which increases with k, with the number, the k again is the number in how many tasks you split, right? Your number of tasks. But then this n over k is the size of the task. And this decreases with k, because delta and n are constant. And so this first is the parallelism, and the other one is, the first one is diversity, and the other one is the parallelism, because you are increasing parallelism by increasing k. And interestingly enough, when you find the optimum k, it depends, of course, of n, because that's what you are splitting. But it also depends of just the ratio between this shift of your exponential and the expectation of the exponential. So how the tail and the shift are related to each other. So there is a trade-off. So there we may have, we have a code of some optimal rate for this model. All right. Now for the additive, that becomes a little bit maybe more, definitely harder and maybe even more interesting, is the task execution time is relance with parameters S and W, because your exponential that you're adding, the computing units, they have expected time W, but then the shift is S delta, because you're adding S of these exponentials. Again, you're splitting your job of size n into k tasks. Each one has size n over k. And then, of course, you can write these order statistics by definition and evaluate them numerically, but somehow, you know, we were not happy with that. We really wanted to gain some intuition in what's happening. And here I can tell you a game which actually describes what's going on here. And you may maybe take a little bit time to think, but then I'll go back to the real problem. So I have 12 players that take round-robin turns in tossing a single coin. And tossing rounds are repeated until some stopping rule is satisfied. And I'll give you these possible stopping rules that you can pick from. So the players are given a set of stopping rules to choose from, right? And the goal is to minimize the expected number of these rounds. And there are, these are the possibilities. One is each player gets at least one head. So that's a stopping rule. So there are 12 of them, let's say L is 3, so 6 of them. To get each one gets a head, so that's one stopping rule. Another is any one player gets 2 L heads, and the third is any L players get 2 heads. So what's identical in this? Why is this that at the end you know that you will have 2 L heads. Either each player gets 1, or L of them get 2, or one of them gets all these 2L. So anyway, 2L heads have to appear, at least 2L in the system. And so what would be, instead of asking you what would be the one you choose, maybe it's an easier question to ask, what would be the one you wouldn't choose? So I'll give a few seconds for people to think. That's
one quick question, Emina. So this example is related to the Erlang distributed scaling, right?
Yes, but even if you didn't hear anything in this talk, especially you or people, or if you just heard up to the order statistics, right? Because there was a coin tossing example. Now I have 6 people here, and they are tossing. The first round, I tell them, toss your coins. And keep tossing after some stopping rule is satisfied. And this stopping rule can be the following. One rule is each one of you has to get ahead. So you just keep rounds are going until they all get ahead, at least one head, until the last one who would get one gets it. Then another stopping rule is one of them has to get 6 heads. And the third one, each one has to get 2. Right. So in any case, I want to see 6. So there is a chat here. I don't know.
Yeah, I don't see any questions in the chat yet.
Or answers.
No, no question.
Yeah. Which one is a bad one?
Oh, I see that Zeev has a question. Zeev, do you want to unmute? And
I just have a guess, which I sent in a chat just to Emina, so to not spoil. But
okay.
My guess is 2 seems pretty bad to me, and I would, if I had to guess, I'd say 3 is best.
Okay, so I think that's good. So why 2 is bad, right? Do you want to say, or shall I try to? Why don't you say it?
Okay, I didn't think that hard. But 2 is you need yeah, 2 is like the minimum of lots of Erlangs, but each of those Erlangs is pretty long.
Yes, exactly. And even if they're not Erlangs, what happens here is that I don't know if it's a good hint, consider a large L, but when you add many things, no matter what they are, they concentrate around the mean, right? Many independent things, or many not too dependent things even. When you add them up, they concentrate around the mean. Therefore, this replication, which is maximum diversity, is not going to be that helpful. So that's one way to think about it, but maybe everyone has his own way. So let me try to maybe kind of illustrate or sort of prove some of these. So here is a quote from Polya that any problem of probability appears comparable to a suitable problem about bags containing balls. So now here, maybe that was my wishful thinking, or that's something how I managed to prove some of these things. Of course, I could have gone with these sums, but I wanted what we called finite length analysis in coding, something for concrete ends, right? Not asymptotically. So here I have n players have independent clocks that, and the clicks happen, inter-arrival times are exponential, right? And they have mean W. And the game is over when one player gets m clicks. So over there, n was 2L and m was 2L, right? And 2 is chosen on purpose because it will be clear later over there, for an example. So now I actually plotted these 4 things randomly, and even just 3. players, the fourth one came kind of similar, although there was lots of differences. And if I continued, they will be all, they will kind of compensate for each other, and at the end, if M is large, they would be kind of similar. That is sort of the intuition, but we should not get that too far. So this is how I'm going to prove it. So T1, T2, and so on, these are time epochs at which any player gets a clock tick. And TBM, so now the notation is a little bit iffy, but it's a time epoch when a player gets M clicks, any one of them. So these clicks are happening, and I say I got a click, and then again we are waiting, and Gauri says I got a click, and so on. And at some point, one of us said, "Oh, I reported M clicks," and that's when we are done. And both this TBM and BM are random variables. So how many rounds and also the duration time, because inter-arrival times are random. And if one of them were not random, it would be really an Earth and Paul's problem. But then we have the Waltz inequality. So if we represent this TBM as a sum of interclicks, so the first one will get T0 to B0. And that is the first click, and so on. And then what I'm left with is, instead of TBM minus T0, or just TBM, I have this addition of exponentials of inter-arrivals. And so both how many they are is a random variable, and this interval is random. And so these are independent and exponential, the intervals. And they're also independent from BM, right? Because how many I wait for the clock does not know about, right? And so I can say that this is equal to exponential of BM and times W over N. W over N is the minimum order statistics for the exponential. And this expected of BM is something that I am going to compute by using something called generalized Brodey problem. And it has analogy. I'm going to use that analogy, and some of you may know it as a coupon collection. So this is the problem. We are looking for the expected number of draws from N coupons until one of these coupons is drawn M times. And these are draws with replacement. And this is known for many years now. And there is some of my colleagues, Larry Shepp and Leo Flato, worked on this, and everyone was telling me, oh, this was my first paper at Bell Labs, etc. In connection with something else I was doing that was using these results. But there is this result from Klumpkin and Newman, again, from that time, that says you can, there is an expression for these, for fixed M and large N. For us, both M and N will be large, but M can stay fixed, right? And then, since they're large, this is easy to approximate by Mn. This through Stirling, this gamma in this region is about 1, and this, of course, if M is large, this is about 10. So this is exactly what we could have said, by just looking at sums of any random variables. Nevertheless, there is this result here. And since we have from the previous slide to divide by N, at the end we get that replication takes order of W, which is the exponential thing order of M. And so job completion time for splitting is log N, because this is just maximum of the exponentials. For replication is order of N, so bad. But then can these can this be, and Ziv actually said correctly, can coding at least sometimes, at least in this case with 2, be better? And it can, and then we can show that this, when you use coding with rate 2, so now each one has to get only 2, but only L of them have to get only 2. then there is a stochastic dominance. And instead of, because we are nearing sort of the end of the talk, instead of going through this mathematics, let me do a simulation, well, kind of animation. So remember there we had 6 players, and I ask you, is it better to wait that all 6 of them get a head, or that any 3 of them get 2 heads, right? And so here, I'm just going to replace this by exponential intercompletion times. So here is 6. Here on the left-hand side, any 3 of 6 should get 2, should complete 2. And here is all of them have to complete. So of course, here will be lots of hand waving, but there is the paper there. So here, they all start, right? They all start, and now they're statistically identical. So the expected time of finishing on left and right is the same, right? There is this one that finished. And at this point, I'm going to tell to the left hand side, Rutgers, stop. So that's why I'm going to say that on the left hand side, even with stopping, this system cannot be worse than the one on the right. So I'm going to tell him, stop, don't move to your other task. And then another one finished. So the systems are still stochastically identical. The other one finishes here on both sides, and I am going to tell this one stop. And then the third one finishes, and I am going to tell them, okay, now let's all of you stop, and let's me send these people home, this here, and these 3 here, and these 3 can continue working. So now I have the same picture on both sides. So with this stopping and sending this on the left-hand side people home, I still am doing at least as well as this. Of course, one has to show that probabilistically. Right? These are the results. And just a few words to mention what other problems, and then I'll take questions at the end. We are looking at why is in practice so hard to think about using coding? One is fear of cost. And this is this notion of redundancy. Why are we putting something that uses more resources? Especially in computing, we have these stragglers because people are competing with resources, and now you're going to increase that competition, right? And another one is what I call power of RQ. And this is that we say, okay, I'll deal with this problem when it gets to me. Meaning, if I notice stragglers struggling, I will cancel some of these and relaunch or some such things. And the first one, there is a paper that we have. It's called Straggler Mitigation at Scale. But there was an earlier paper which was attacks of clones. They were saying like introduce redundancy. And then our follow-up paper was which clones should attack it and when. Meaning, do I need to use coding or should I use just replication, like the simple clones, simple cloning. And it turns out that that you can answer some of these questions. So these are, I'm not going to get into that now. And then this is something I call latency cost boomerangs. Depends also on this fear of cost. There are distributions where, yes, by increasing latency, Gauri has worked on this, by decreasing latency, you will increase cost at some point very much so. But then there are these heavy tail distributions where increasing redundancy will make you decrease both latency and cost up to a certain point, and so on. In canceling and relaunching, yes, that's a good thing. And that's what's done. But still, maybe practitioners need to know when to cancel a task, right? Because if you are canceling too early, you may be canceling non-stragglers. If you are canceling too late, then you will incur more cost, etc. So some such results also we looked into. Does excessive redundancy hurt performance? Yes, it may. And I just wanted to say that, yeah, we have just scratched the surface of some of these questions. These last few that I mentioned here are in this paper, Straggler Mitigation at Scale. This analogy that I try to make here is that suppose you have to have some job done and it needs to be, some people need to go somewhere. And instead of counting on only one, you may send several of them for the same task and one of them will finish. But if everyone is doing that and you are sending too many, then, you know, if you have a little bit more cars on the road can handle it. But at some point, all sorts of other things will come. First, you may come to a standstill. Some people can get really upset, start quarreling, etc. So, and then there is this paper, Diversity, Parallelism Trade-off, which we wrote kind of during the pandemic time. And then recently with Alex Princeton, we started looking into some of these things again and just got an NSF grant to look, but some things seem hard, so I don't know how much, but it needs someone like you here in the audience who are better at these things than I am to look into. So I was told to leave a few minutes for questions. So that's...
Thank you very much, Emina, for the great talk. Are there any questions from the audience? Feel free to type them in the chat or unmute yourself. Yes, while people are thinking, I can ask a question. So in the table, the summary table that you showed with the different distributions and different scalings, I noticed that for the bimodal distribution, as the tail gets heavier, first splitting is optimal, then coding becomes optimal, and then again splitting becomes optimal. So I was curious to see why that happens.
Because if you look at the binomial, and binomial actually, many of these, some results are numerical, of course, but binomial, we were able to get some with the lots of large numbers, because binomial is combinatorial, right? So what happens in the beginning is, so at the end, I mean, when you are very likely not to have stragglers, and you are very likely to have stragglers, then these are the same situations. So in the beginning, everyone is finishing at one low epsilon. Everyone is finishing here. So I better split among them. But then if it's very bad, then everyone is finishing at B. So I better split among them. So there is no randomness, in other words.
Oh, okay. See what you mean. And then in between coding as well.
Exactly.
Right?
In between, there is some randomness, and you want to diversify and you want to remove some of them. But as soon as you don't have randomness anymore, which surprisingly here kind of happened at the end again, at the end means when epsilon is large. So here, whether the epsilon is large or small is...
Makes sense. Okay, thank you. There is a question in the chat about the different scaling models. Pranay is asking that in the context of grocery shopping, he understands how the server and data dependent models work. But could you explain again what is the additive model and what it would mean in, say, a grocery shopping context?
So an additive model would be that, especially in some stores like Trader Joe's, etc., each item, somehow the cashier looks and says, oh, this is boring, let me just scan it. And then another one, oh, did you ever have this? I really like it. I recently discovered it, you know. So each item is does not really is independent of what was of what was before, or it, you cannot really predict what that particular cashier was. So you're in all of this you're adding things. But we call this additive just basically saying that each of these units is independent of the previous one. So maybe let me just see which picture would be good for that. Maybe this one. Maybe this one. So, so in the additive, each item, you really don't know whether this server cashier will take a long time to scan it or not. Maybe for some other reason, it may be that in the middle there is some price check or bathroom break or something like that that happen, or the cashier just likes it or wants to read something. Or again, Trader Joe's is the best probably example for this, because they charge you by the number. So then they have to count tomatoes, right? Whereas if it's just inside the bag and they're not transparent or something. Whereas if it's just crackers, they will just scan it. If it's server dependent, then the server will chat a little bit with you in the beginning. No, if it's data dependent, and then split everything and so on. I don't know if this additive explanation in the grocery store makes sense.
Yeah, this makes sense. I mean, it would be something like if you have a size S task, it's as if you're doing S smaller tasks sequentially, right?
Yes.
Like yeah, that's why it's
exactly. In all of this, I'm doing this task sequentially, this computing unit sequentially, but how much each takes, it may be some sample of a random variable that the server made, or it may be constant, but still there is some randomness in the beginning. Because if there is no randomness, there is no trade-off for diversity. So.
Okay. Thank you. Are there any other questions? We have a couple of minutes left. I'll ask one more question. So in the results that you presented, there was no queuing of tasks at the servers,
exactly.
right?
Not at all.
So if there was queuing, I understand that it will become really complicated to analyze because it will become fork join queuing system. But do you have any insights on like how the coding gains would be affected if there was queuing? Will it be diminished or increased?
Yeah, I don't actually. Oh, there is something else that I'm not going to be able probably to explain well. And this is if certain things are done in batches, they are probably not, and you cannot send feedback. So now these are computing units, etc. But instead of that, I have batches of tasks. It depends on the coding rate how big these batches should be. I'm willing to talk offline more about that. We did some simulations and some analysis, but we thought it was very interesting, but could not make sense out of it. And yes, these are all fork join. It would be fork join queues, but then I remember when you, Gauri, and I, like some 10 years ago more at Bell Labs, we looked into some of these problems, and until they told us this is actually probability called fork join, we were able to derive some results. Like, oh, sorry, we didn't know it was hard. But no, actually, some sub-problems, because of the redundancy, turned out not to be hard. And some bounds, which people knew about, turned out to be tight. I don't know if it's the best characterization, Gauri, you know, also. But no, I don't really have much intuition how hard it would be.
Thank you. I think there are no other questions. So okay, let's thank Professor Emina Soljanin again for a wonderful talk.
Thank you.
Thank you. And her slides will be posted on the website. The talk recording will also be available on YouTube later on. And yeah, we'll see you in a couple of weeks for the next talk. Thank you. Thanks, Emina.